Hi everyone. Uh, we are on the session 7 part 2. Just to give you, there were some pieces we had missed and some additions we made to slides on the part 2. And so I'll just walk through on the session 7 supplementary, we call this, or we can call it as part 2 of the session 7, where I'm covering the missing pieces. And this is related to obviously the first presentation on the part 2 of quantum circuits and gates. And here the coverage was uh, planned to be quantum register, quantum data processing, entanglement, build state, and EPR paradox. 7374 entanglement and build states and EPR paradox uh, was missing from the recording as pointed by one of the attendees. So I'm going to talk about it. Prior to that, I'll just get to the uh, register, quantum register, where we had pointed out something on the qubits, and the qubits were represented by electron. I am also adding photon to it. So the spin up, spin down uh, of the classical corresponding in terms of bits were bit to qubit, and so just to make sure that the classical and the quantum qubits are different, and obviously they occupy different memory requirements are different. However, that was what was pointed then. And there was one more thing which where we had talked about the qubit n, small n, and then the number of basis vectors which were n capital N. And so if we have to find out how many other mixed states are there other than the basis states or basis vectors, we have to really do a permutation rather than combination. So we have to take n to the power n. So if you have two qubits, then 2 to the power 2 4, and minus the actual 2, which is 2 to the power lower n, which gives you the that for a one qubit you have got two other mixed states and two pure states. Same way for two qubits, you should have number of basis vectors being in this case. Two qubits will give you four states. So if you take 4 to the power 4, which will give you something like 256, and out of which 4 are pure, so you are left with other mixed states which are 252, and they may be entangled from 0% to 100% depending on maximum entanglement. That may vary. For 3 qubit, for example, if you have 8 number of basis vectors n, uh, then correspondingly you got mixed states something in the 16,000 range. And same way for 4 qubit, you will get something like uh, it's pretty much millions, I think. And then I have to just write it correctly. So it's 4294967 which is so there are many mixed states for a uh, for a small n qubits are corresponding capital N number of basis vectors. Um, so accordingly, this is the formula n to the power n, which is n caps n stands for the number of basis vectors, and uh, 2 to the power n, which stands for the basis vectors. So you will find that other mixed states can have uh, possibly uh, something non-zero, what you call the entanglement. Now, how much of non-zero entanglement will depend upon the the combination thereof and how the environment is there and how these are entangled, etc. So moving on to the next slide, I will go into this quantum register data processing. We just wanted to mention that 7.2 in the data processing, um, B10 represent as basis 10. So instead of saying binary, we can do the 0, 1 to 15 presentation. That was what was intended there. Then the other portion here, I can move on to um, the entangled state here, and hopefully this should give you much better uh, picture of what we were. So we were talking about entangled build state. So the four entangled build states which are entangled, maximally entangled, is uh, 1 by root 2 1001 and 1 by root 2 100 minus 1. This is called 5 plus and 5 minus. And same way uh, the 5 psi plus and psi minus 1. Now how these are arrived, we can look at it. So generally we can this coverage we had not done at that time because we had not really gone through the Hadamard gate. So now that uh, we have gone through Hadamard gate, the question is how do you generate build state? So build states can be generated by taking a Hadamard of the input and doing a C naught. So or we call it as C naught of Hadamard transform gives us 2D entangled state, and it can give for any entangle, any number of uh, qubits. But we will present here for 2 qubits because that's the one which gives us the easiest way to understand build states. So if you look at this gate, which is a Hadamard gate, and followed by a what you call the C naught gate. So if you have a Hadamard gate and you give input 0, and to the second wire you give the ket 0, so both of them are ground states, and when you it passes through Hadamard, and obviously when you pass through Hadamard uh, ket 0, it just rotates, and then you get a what you call the a ket 0 will produce a ket uh, plus state, and similarly when you have this ket plus state, which is represented by in terms of ket 0 1 presentation, it's called as 1 by root 2 ket 0 plus 1 by root 2 ket 1. When you then apply a C naught on the ket 0, which is the input here, what would be the output? So because of the application of C naught, here what happens when you have this at this point, when you have a Hadamard of ket 0, which is this, and again uh, a cross product, sorry, a tensor product with ket 0 will give you what? 1 by root 2 ket 0 0 plus 1 by root 2 ket 1 0. And if you apply C naught, then at this point, what will we get? So at this point, we will get the 1 by root 2 ket 0 0 plus 1 by root 2 ket, this 1 gets flipped to this. Because of this is 1, this next bit gets flipped, which is a bit flip, so it gets a 1 1. So basically what happens is we get a 1 by root 2 ket 0 0 plus 1 by root 2 ket 1 1. This is the result we get. So this is a maximally entangled state, and we cannot really break this into individual subsystem. And this is 5 plus. Same way, instead of 0 0 we apply 0 1, we will get the similar at this interface. We will get 1 by root 2 ket 0 plus 1 by root 2 ket 1, And this time, since we are applying a 1 in this case, uh, so now what happens, since we are applying a 1, you are going to get a flip of 1 to 0. That is the second, the target bit gets flipped by 0, by um, inverted, that is it gets flipped. So therefore you got this 1 by root 2 0 1 plus 1 by root 2 1 0. This is somehow represented as psi plus. Both of these have a plus in between, but this is phi plus and this is psi plus, standard representation. Same way, instead to the same circuit, if you give 1 1 as the input and 1 0 as the input, the Hadamard transform this 1 ket 1 into which is nothing but x basis representation, from a ket1 represent x basis, and which is now normally we call it as minus, but if you look at minus in components in terms of z basis, then it is 1 by root 2 ket 0 minus 1 by root 2 ket 1, and then you are doing a cross product with ket 0, so that results in 1 by root 2 ket 0 0 minus 1 by root 2 ket 1 0. And if you take a C naught of this, then obviously this flip of this one, this is their source, target 0. So target will flip here, so it becomes 1 1. So you get a 1 by root 2 get 0 0 minus 1 by root 2, and this is represented as phi minus. Similarly, when you apply a ket 1 to the same gate, you are going to get what you call um, 1 2, you are going to get minus, therefore it is this, that is ket minus is nothing but 1 by root 2 ket 0 1 minus 1 by root 2 ket 1, and if you take a c naught, because you are getting a 1, so the second bit will flip, so it will become 0, so you are getting 1 by root 2 ket 0 1 minus 1 by root 2 ket 1 0, which is psi minus. So bill state using Hadamard and c naught are easy to generate, provided you can input to the 2 wire, the 2 qubit, get 0 0 ground state, get 0 1 1 0 and 1 1, and that is the corresponding phi minus phi plus psi plus phi minus psi minus, the 4 Bell states. Now what happened is, these Bell states which we generate, um, this has a relevance in communication. So generally what we say is, if we want to uh, clone, which is not allowed as per the quantum mechanics and quantum theory. So you can't clone, like copy paste and transfer. That is what we do in classical computing. That does not happen in quantum. So you use a process, and that process we will discuss later, called teleporting. But essentially, what it boils down to is what we saw recently. This Bell state is what is a classical uh, 2, which is different from classical here, because here you got the uh, superposition and mixed state entanglement, and it can be from 0 to 100% as it is maximal, that is, and this is the maximal entanglement for any qubit, any number of qubit, uh, with a combination of inputs which we give. So here what we show here is Einstein, Podolsky and Rosen, uh, they had uh, they had at the time in 1935, when these things were projected, had strongly objected to this spooky, that is, if I send something and then uh, if someone at this end, like Alice sent something to Bob, both of them source from the same, let's say, source, and then Alice and Bob, Bob carries the entangled qubit, Bell state qubit, along with him somewhere. He's on a, let's say, a mission to some galaxy. So let's say they met in Palo Alto in 1900, January 1, and derived an entangled qubit, Bell state qubit, as we showed last slide. And if they carry with them, Bob carries one of them, he lives with the same qubit as, let's say, 5 plus. So if he took 5 plus and he went to galaxy, um, it may take 100 years, let's say. It doesn't matter. Time, infinity time, we can assign to it. But not infinity, but finite time, let's say 100 years. Because we are measuring in terms of light, and so light years. So we want to make sure that there is sufficient time. And uh, Alice decides, God gets curious, she decides, let me measure what I have. So she measures and she finds that she has a uh, the state of the 5 plus. She discovers that she has a ket 00. So when Bob, according to the theory of quantum, it should, because it is um, same qubit, entangled qubit, when Bob measures at his end, whenever he decides to do that, it should be 00. So this is something unexplained, because uh, according to Einstein and uncertainty principle, there is an uncertainty, and you are measuring something uh, at a time which is far off, as well as it's, that means it has, the possibility is that you have to this, whatever the variables which cause this, hidden variables which they termed, and they said that if there is a hidden variable, a local variable at Palo Alto where Alice and Bob met, that hidden variable must have traveled along with the uh, Bob's entangled uh, 5 plus. That's why when he tries to measure, it will give 00. So they call it as spooky variable at the distance. So they had postulate, or they had at least written a paper stating that this cannot be possible, and therefore quantum mechanics in itself is uh, not correct, or it's not meeting the laws which they have framed or they have conceived. So, but this is not true, because after that, 1965, Bell took the EPR paper and said that if that is the case, then uh, either the, if the hidden variable exists, then we must be able to prove that um, the this is it cannot, either we have to say that it can travel faster than the speed of light, and then therefore the hidden variable carries it. But if that is not true, then the hidden variable theory is not correct. So essentially, one had to prove through probability that Bell, actually Bell in 1965 wrote based on some probabilities that this cannot happen, because you cannot have probability greater than 2, whereas with this 1 by root 2 and all that, it appeared that the probability based on the computation comes to 2 by root 2 root 2, which is greater than 2. So then that's something uh, for the 4, I mean to say the 4 qubits, because each one of them zero point 0.5 into 4, because Bell states are 5 plus 5 minus 5 plus 5 minus. So you are not expecting more than zero point 0.5 into 4, which is 2 max. But it turns out that he proved that it is 2 root 2. He said, therefore, that hidden variable theory is not correct. It does not travel faster than uh, speed of light, and that this is the nature. And then that was subsequently proved by several of these scientists like Alien, John, Anton, and all these got Nobel Prize in 2022 for debunking the uh, hidden variable theory. And that's called as Einstein Podolsky Rosen uh, what you call the um, paradox. So ultimately, uh, what we want to uh, say here is that you can do a measurement not based because the logic or the argument there given was by EPR is that if you measure in terms of plus minus 1 on the Bob's end, whereas Ellis end it was made in terms of kids 0 and 1s, then you are going to get obviously a different uh, argument. That is, they are not in the same basis, so they are going to get different. But that's not the case, and therefore it got proved that it does not violate any of these uncertainty principle and all that. So yes, of course, Einstein is great. He had his MC square along with the Satyendra Bose, Einstein Bose, and various other equations. And he was also uh, he also worked along with Oppenheimer, which recent movies you would have seen, Father of Atomic Bomb, and on this I am recording on a date, August 10th, which is 9th, 6th and 9th were the day when um, the atom bomb was dropped. So obviously, with such a great background, Einstein, for last 20 years of his life, he could not figure out the paradox. And then it was John Bell, and therefore this is a very popular one. One can also prove using probability theory. Yeah, of course, there are many videos out there in the YouTube. You can watch them. But essentially, we needed to cover this EPR paradox, and that's what I have brought here. And so this should cover the balance of this. And teleporting we'll see in the upcoming schedule for next week, which is on the August Monday. That is Monday, this coming Monday. So we'll cover part of teleporting there. And with that, I will stop the recording. And this recording will be added as supplementary to part session 7. Hope that resolves the missing piece which we had requested. Thank you.